In the last lecture, we discussed the nature of light. We'll take our discussion further in this lecture, where we'll discuss, is light a wave? At the very outset, we'll discuss when should we use geometrical optics. Then we'll address the question, when does wave property dominate? And how does the wave property originate? And lastly, what is the basis of wave-particle duality of light? So first, why not geometrical optics? Let us consider the source of light, the sun. So sun emits light, and that light reaches earth, which we can call the sink, and the time for light to move from sun to earth is 8 minutes 20 seconds. Now light moves from sun to earth as a ray, or what we call photon, which is a bundle of energy as emitted by light. Now we can determine exactly the location of the star just by following the path of light. In other words, just by moving along a straight line which we suppose light has followed in its journey from sun to earth. So this shows that light travels in a straight line. Now let us ask the question, what about the wave character? In the laboratory, we do optical measurements, and to do various experiments, we use certain apparatuses in the form of lens, mirror, prism, telescope, and so on and so forth. Now in all these cases, two dimensions or two lengths come into the picture. One is the wavelength of light, supposing wave character, and the linear dimension of the instrument that we use. Now if you compare these two lengths, the dimension of the apparatus is far larger than the wavelength of light. So compared to the dimension of the apparatus, we can set lambda tends to 0. In other words, we can ignore the wave property of light. So in such situation, we get a pencil of light, or what we call a ray of light, which is represented by a straight line. And this is referred to as rectilinear propagation of light. The question that we'll address soon is, if this is so, then when does wave property dominate? Now before coming to that, let me remind you about the laws that you did in geometrical optics class. Some of the laws are rectilinear propagation of light, law of independence of light rays, principle of reversibility of light path, laws of reflection, and laws of refraction, as well as the Fermat principle, according to which integration n dl is stationary, or equivalently the variation of integration n dl is 0, where dl represents an elemental length traversed by light in a medium having refractive index n. Let me now define what we mean by optical path, because this will be used in physical optics also. Optical path is also called equivalent vacuum path. So if we consider a medium having refractive index μn, in which suppose light traverses a distance L in time t. Now optical path refers to the distance in vacuum which light would have traveled in time t, that is in the same time t, and therefore it is called equivalent vacuum path. Now in time t, light travels a distance ct in vacuum because in vacuum speed of light is c. Now since in time t light travels a distance L in this medium where the speed is v, it follows that t is L by v. So we have t equal to L by v, and therefore we can rewrite it as c by v into L, and define refractive index of medium as ratio of speeds of light in vacuum and in a medium, and therefore we end up with μm for c by v multiplied by L, and this is called optical path, which is abbreviated often as O dot P. Here the refractive index being c by v, and since v is less than c, or rather c greater than v, μm is always greater than or equal to 1. Equality sign holds when we are speaking of a vacuum in which v equal to c, so c by c is 1. In other cases, when we are speaking of a medium, v is always less than c, making μm greater than 1. Let us now address the very important question: when does wave property dominate? Let lambda be the wavelength of light and d be the dimension of an aperture or slit or an obstacle, say. So this is the wavelength of light, and this is suppose the aperture or the size of the slit. Now let us consider the case when this d is much larger than lambda. So in that situation, lambda being small, lambda is nearly equal to 0, so we can neglect lambda. Now lambda represents wave characteristic. If we overlook lambda, that means we are overlooking the wavy character of light and assuming that light propagates in a straight line. So in that situation, we will say that light follows a straight line and behaves as a ray, and in this situation there is no bending or diffraction. In this situation, here is the aperture or the slit, this is the source, and these are the pencil of light, they move straight. So this is the illuminated region, and we have well defined boundaries defined by light. But if it so happens that d and lambda are of the same order, that is aperture size or obstacle size is comparable to the wavelength lambda. In other words, wave property is important now because now lambda has to be respected. Lambda is important now, it cannot be ignored. Since wave nature cannot be overlooked, and wave means there are ups and downs, there are undulations, it automatically means that light will bend. There will be bending. Now let us consider this diagram where this is the light source which emits light. It hits the aperture, and if it so happens that it goes straight, then it hits the screen here, which means we'll have a perfect shadow in this region and in that region, while this region will be the only illuminated portion, perfectly illuminated portion. But this doesn't happen. What happens is shown in this following diagram. Here is the light source. Light is moving and it hits the aperture. This is the aperture, and at the aperture there is bending. So light bends into the shadow region. So light enters into the shadow, and therefore we have a greater amount of illuminated region. Actually, there are no well-defined boundaries then between which one is shadow and which one is illuminated region. So bending of light exhibits wave nature. Let us consider a similar diagram here where we have shown an obstacle. So light source encounters an obstacle which has dimension of the order of wavelength of light source. In that case, light will bend as it tries to negotiate the obstacle, and therefore if there was no bending we would have shadow of this amount, but since there is bending of light, light will enter into the shadow region, and therefore we will have blurrings at the edges, and this region, the shadow which we are calling, will not be perfectly dark. A slight illumination will be there, and all this is due to bending of light. So in other words, wave character is manifested in these phenomena. Let us now address an extremely important question. How does wave oscillation come up? In other words, what is the mechanism of wave oscillations? Let us consider a positive charge and a negative charge, and we'll consider their movement. The positive charge comes down and negative charge will move up. So we'll start from here. At one instant they are separated. The positive charge separated from a negative charge, and the electric field line that is generated is this one, directed from positive to negative charge. Now positive charge moves down and negative charge moves up, and therefore the field, E field, is reduced. The process continues, and ultimately at some time positive charge and negative charge are occupying the same point, and then we cannot draw this E line, which means E is 0 here. And then what happens is the positive charge continues its journey downwards, negative charge continues its journey upwards, so that E line now is directed from positive to negative and it is upward. Earlier it had been downward. The process continues and the lines increase in size, and ultimately we end up here where negative charge is on top and positive charge at the bottom. The separation is maximum as in this situation. The negative charge now moves down and the positive charge moves up, so that the electric field now diminishes to be 0 at this point. The process repeats and we have this diagram. Clearly, such movement of positive charge and negative charge up and down, that is along the vertical direction, generates an E field, and this E field is oscillating as shown in this diagram. Here E is negative, it decreases from a maximum in the negative direction, and at this point E is 0, and then the field lines, E field lines, will increase. It reaches a maximum, it is positive in this region, and then again it decreases but positive. At this point it becomes 0, and then it becomes negative in this portion, and here it is maximum negative, and the process repeats or continues. So in a nutshell, If we consider movement of positive charge and a negative charge up and down, that is vertically, then an oscillating E field is generated. Now let us consider how does a B field generate. Let us be reminded of the fact that charge moving up and down means current. Current is dq dt, so movement of charge means current. And again, as per Orsted's observation, current produces a magnetic field or magnetic induction B. Now take a wire and send a current in it. Suppose current moves from up to down. This can be looked upon as a charge heading down, a positive charge moving down, and a negative charge moving up. And this positive charge and negative charge, movement of them in a vertical manner, was discussed just now. So these two situations therefore are equivalent. Now this current I that moves down generates a magnetic induction whose direction can be determined from right hand screw relation as indicated. We can check it easily. So B is here. If current is down, B is in this direction. Now as plus and minus, they are upon each other. Earlier we had field 0. Now in this case therefore we'll have I equal to 0, and since I is the source of B, the magnetic induction will be 0 also. So when charges are separate, we'll have a current which produces a B field. As the distance between charges varies, they diminish, the B field will also diminish, and ultimately it becomes 0. Now what happens is plus and minus again starts to move but in opposite direction, and therefore we'll have a current in opposite direction which in turn produces a magnetic induction whose direction is opposite. So current changes direction, becomes upward, and B is developed in the opposite direction. In other words, B oscillates in time. The rule to find the magnetic induction vector B is as follows. Take your right hand and place it along the direction of I, and then curl your fingers to form a circular track. Then the tangent to this track, to this circle, gives us vector B. Now the directions of E and B are shown here. E was earlier shown to be in the vertical direction, and B, as shown in the diagram just now, is in the xy plane, and the direction is determined by the right hand screw relation. Speaking in a nutshell, E corresponds to up and down oscillation, and B, being in the xy plane, we can take it to be in and out oscillation as shown here. So these are the B oscillations. So this is up and down oscillation of E, and these are the B oscillations which is in and out. Now let us draw the diagrams of E oscillation and B oscillation together and then wind up. So this is the diagram. These are the E oscillations, up and down movement of E, and this is the B oscillation which is said to be in and out movement. Now the basic idea is as follows. Changing electric field generates a magnetic induction, and a changing magnetic induction generates an electric field, and they balance out in such a way that we have a coupled set of electric field and magnetic field that is moving along K cap. One thing is to be noted that there are no charges here, there are no wires here. It is the fields that are moving, and initially they were generated by movement of charge, but now they are self-contained, they are moving, and they propagate on their own, they oscillate back and forth because E creates B and B creates E, and this is called electromagnetic wave. Now in this diagram, or from this diagram, it is clear that E and B are perpendicular, as well as both the fields are perpendicular to the direction of propagation, and E, B and K, they form a right-handed screw relation. Now this fact that the fields are orthogonal to the direction of propagation is referred to as electromagnetic wave being transverse. So this is transversality of the field vectors. They are both transverse to the direction of movement or the propagation vector. Now an important thing is that in 1676, Romer, in 1849 Fizeau, in 1850 Foucault, and other scientists at other times determined the speed of light, and it turned out to be 3 into 10 to the power 8 meter per second, and is denoted universally by c. Now this same c, which is the speed of light, this same c was reproduced by Maxwell in 1864 in his Maxwell's equation, which coupled the electric field and magnetic field through these four well-known and famous equations. This E was given by Coulomb's law and B by Ampere's law. Here rho total is the total charge density, J total is the total current density, and very importantly there are two constants, epsilon 0 being the permittivity of free space and mu 0 being the permeability of free space. Now these constants can be coupled in this fashion. So the constants mu 0 and epsilon 0, when combined properly, give us 3 into 10 to the power 8 meter per second. See, so these are the calculations. We have put the value of mu 0 and epsilon 0 properly, so it straight away gives this numeric, which is 3 into 10 to the power 8 meter under root Henry into Farad. And Henry into Farad, if we follow the standard procedure, if we use these equations, phi m is Li and Q equal to Cv, here C is capacitance whose unit is Farad, then we end up with simply second. So under root Henry into Farad, we can show that it turns out to be second. So the speed of light follows from Maxwell's equation, where field E and B were being discussed. So E and B fields therefore move with c, which is the speed of light. In 1873, therefore, through these calculations, Maxwell established the electromagnetic theory of light, the essence of which was that light is a transverse electromagnetic wave. The E and B fields associated with the wave satisfy Maxwell's equations. A wave means light wave. which is essentially an electromagnetic wave as shown by Maxwell's electromagnetic theory. This diagram shows the electromagnetic spectrum. Here nu is increasing and here lambda is decreasing. The electromagnetic spectrum is fairly long range and will be concerned with the visible portion only. So this is the portion which we will be concerned with, but to get a rough idea, we have shown the electromagnetic spectrum. This region is the radio wave in which our TV, FM radio, AM radio, antenna, discs operate. This portion is microwave region where we heat food in a micro oven. Also remote sensing, Wi-Fi, mobile phones, radar, these are operated in this region. And CMBR means cosmic microwave background radiation. This also falls in this region. CMBR is a relic of the radiation that once dominated this universe just after Big Bang. We will not go into details of these here. Just a passing comment is being made. An infrared region is again a very important region. Humans at normal body temperature radiates, and this radiation falls in infrared region. Also, if we consider an ice cube or a hot charcoal, then the radiations they emit will also fall in this region. Satellite records data using infrared also. In the visible region, we can use lasers. In ultraviolet region, we can use UV lamps and also devices that kills bacteria or microbes. X-ray is used in radiotherapy, it falls in this region, and gamma ray is here, the source being neutron star, pulsar, supernova explosions, and in radioactive decay we know we get gamma. Now this diagram has been drawn not to scale firstly, and secondly the nu value and the lambda value may not match. There are no hard cutoffs here and the values are just indicative. Let us now point out it is the same electromagnetic spectrum redrawn here, and with it we can explain the basis of wave particle duality that visible light exhibits. Actually, this end of the spectrum where gamma ray is there, it behaves like particles and it does not behave like a wave. This is evident because here nu is extremely large. A large nu means h nu is very large. So effectively, since h nu is very large, effectively things are discrete. That is, the photon size are very prominent. We cannot neglect the photon structure. While on the other end of the spectrum, nu is very small. This end of the spectrum where we have radio wave, microwave, they behave as wave. They does not look like particle. This is extremely evident if we consider the concept of h nu. Nu being small, h nu is very small, so that effectively the structure is continuous. Photon is not important in this end of the spectrum. Now visible region lies in between. It is sandwiched between this end and that end. So it gets both the properties. So light acts both as wave and particle. Any one character will manifest and which one will manifest will be decided by the experiment we perform. So this is the basis of the fact that in this region wave particle duality is dominant, is expressed. So light exhibits wave particle duality. Classical optics means there are two branches. One is physical optics, one is geometrical optics. And in this discussion, we have emphasized that this is the route to go from physical optics to geometrical optics. If we put lambda equal to 0, then we are in this region. But if we consider lambda, then we are in this region, which is the domain of wave optics. So in physical optics, we'll take that light propagates as a wave. We'll consider light to be moving as a wave. And this is a more general picture, because in this picture, if we put lambda equal to 0, we go to geometrical optics or the ray optics. And in geometrical optics, light propagates as a ray. So in physical optics, we'll be concerned with wave structure of light, which was first given by Huygens. The transverse nature was predicted by Fresnel. That light is electromagnetic wave was predicted by Maxwell. Also, Einstein predicted the photon aspect of light, and together they form what is known as wave particle duality of light. Before ending this lecture, let me just re-emphasize that the visible region of electromagnetic spectrum has wavelength 10 to the power minus 7 meters, frequency 10 to the power 16 hertz. This is the photon energy per photon. This is the energy in case of visible light, and these data are extremely important, which should be kept in mind. Light, as we know, produces sensation of vision, and the mechanism is that through the pupil of our eye, light enters, and there is a lens which focuses light in the retina, and the retina contains certain photoreceptors, and the photoreceptors are two types. One is the rod cell, and there are so many of them, 120 million, and cone cells 7 million. This light which falls on these photoreceptors stimulate them, and they send signals to the optic nerve, which goes to the brain, and the brain processes it, and then we can see an image or picture. Let me end this lecture with a quote of Irfan Khan, the great Indian actor. The sign of a good society is where talent is respected. Indeed, talent hits a target that none else can. Thank you.